Welcome to Physics 20 Work Energy Theorem, Lesson 6.2. And the first thing we're going to be taking a look at what causes a change in energy. Now, a change in energy can happen in one of four ways, specifically the energy transfers. Now, hopefully you remember in past courses, we've taken a look at energy transfers. You've got the electrical, which can happen through moving charges, mechanical, that can happen when an object changes position through a force, heating, which occurs when heat is transferred from hot objects to cold objects, uh, or radiation, such as via electromagnetic waves. But in this case, we're talking about in the work energy theorem, we're talking about work happening, which is a mechanical force. And so it's the mechanical transfer that we're looking at within here. So the work energy theorem applies specifically to mechanical transfers. If you want to a refresher on energy transfers, you can pause, scan this video. I'll put a link to this video also in the comments, but this will be a video just as a little refresher. So we've got four transfers: the mechanical, which is forces; the electrical, which is based on moving charges; heating, which is conduction or convection; or radiation, which is through mechanical electromagnetic waves, EM waves, such as light, X-rays, etc. And these transfers operate in a very similar way as money. We can have money stored in a bank, we can have it in our wallet, we can have it in our sofa. But what we're talking about at a transfer, we're talking about things like an e-transfer, or paying cash, or writing a check, or using a debit or credit card as ways that we're moving money from one place to another, right? And again, specifically, with the work energy theorem, in all cases, energy must take a pathway from one energy store to another. In the case of mechanics, it's a mechanical pathway. That makes sense, which means it's caused by a force. And the transfers that we're looking at in Physics 20 are the mechanical energy stores, which are kinetic and gravitational. So mechanics is that branch of physics dealing with motion and forces, which means mechanical energy is the kinetic and potential varieties. Our relevant formulas can be found in the momentum and energy spot. And when we're talking about the work energy theorem, we're focusing in specifically on this one. Work is equal to the change in energy. And what we're talking about is the change in energy between one store to another store. Right? If we're talking about how much energy is lost due to friction as kind of that thermal store, well, we'll say that that energy is equal to the coefficient of friction times the normal force times the distance, which is really just work multiplied by distance, force multiplied by distance, because the coefficient of friction times normal force is the force of friction. Now, common mistake many people make, especially when we're talking about a change in kinetic energy, is that they'll just take, well, the change in velocity squared, which is Vf minus Vi squared, but that's not the same thing, right? Just quickly as an example, let's say we've got a ball that moves 2 meters a second and is becoming a ball moving 5 meters a second. What is the change in energy? Well, first, we're going to use 1/2 mv squared for the ball before it starts, which means 1/2 2 times 2 squared. So it had 4 joules of energy. After this force has moved it and it's now moving 5 meters per second, again, we're using the 1/2 mv squared, and we wind up with 25 joules. So going from 4 joules to 25 joules, you should see that it's 21 joules. But we don't do things this way, where we would just take the difference in the velocities and multiply it out, because that would get you 9 joules, not the correct answer. So let's take a look at example number 1. An archer exerts an average horizontal force of 55 newtons on a bow arrow system, pulling the string back 0.35 meters. If the mass of the arrow is 0.25 kilograms, what is the potential energy stored in the bow? Well, we're pulling this back with the force through some distance. And because we're pulling it back through some force through some distance, we're applying work to it. We're applying that force. And it's going to be stored in the elastic potential energy in the bow, which means that change in energy is the force multiplied by the distance. So we take the force and the distance, multiply them together to get 19.3 joules will be the potential energy stored. Now we're kind of making the assumption that pretty much this is a 100% transference, or at least close enough that how much is being lost to things like friction or whatnot is pretty insignificant. Okay, if it was significant, it would be mentioned in the problem. If we want to find out the horizontal velocity of the arrow, if the bowstring imposes an equal but opposite reaction, so 55 newtons over 0.35 meters, the opposite direction once it's released, well, work is again equal to the change in energy. It's applying that force through a distance that's going to go towards from the potential to the kinetic store. So we're going to isolate V, plug in our numbers, and we find that it is 12.4 meters per second will be the velocity in whatever direction it is pointed in. Now we're just talking about the horizontal velocity, meaning we're ignoring the gravity portion in this, right? The vertical component. Taking a look at example number 2, if we got a 985 kilogram car traveling at a velocity of 12 meters per second, how much work is required to stop it? Well, in this case, it's going to be the change in energy. It had kinetic energy. We're going to have to apply work in order to change this to 0, which means that work is going to be equal to 1/2 mv squared, right? All that kinetic energy has got to go into some other store. So taking a look at 1/2 mv squared, we find that that work is going to be 7.09 times 10 to the 4 joules. Now, when you're stopping a car, where does that energy go? Where is it transferred to? Well, it's transferred to usually the thermal store because of the friction between the tires and the road. But that work, that amount of energy, is the work done. And if we're using 500 newtons, knowing work is equal to force times distance, we can just simply take the work divided by the force to get the distance. So using the full calculator answer, not the 3-digit one that I had before, divided by that 500 newtons of stopping force gets you 142 meters of stopping distance. Okay, again, this is all just based on how much energy is being transferred. If we take a look at example number 3, we've got a student that throws a 5 Newton object vertically in the air with a force of 9 Newtons for a distance of 0.45 meters. What's the final velocity of the object as it leaves her hand? Well, this is a little bit trickier because we are throwing something up. It's from rest. This is going to go into both a potential and a kinetic store, right? This is being thrown up with gravity. And because it's a 5 Newton object, we can find that this is a 0.51 kilogram object. So work is that change in energy, and it's going to both the kinetic and gravitational stores. The 9 here with the force is the force that we're applying to it, the work being done over a distance of 0.45 meters. The kinetic store is that 1/2 times the mass, 0.51, v squared, plus mgh, how much is going into the potential store, right? 0.51 is the mass, 9.81 acceleration due to gravity, and 0.45. So what we're doing here is, first of all, we're going to just simplify the numbers with each term, leaving you with 4.05 is equal to 0.2548 v squared plus 2.25. Subtracting 2.25 from both sides, essentially isolating just the how much energy is going to the kinetic store, and dividing by the mass, or dividing by the 0.2548, and square rooting gets you 2.66 meters per second as being the velocity here. And again, if we think about this in terms of, okay, I'm applying some mechanical force transferring energy to both the kinetic and potential stores, it sets up quite easily. How much work is being done to a change in energy in the stores? Now, because it's coming from a student, yeah, we know that this is coming from a chemical store that's applying some sort of force with the mechanical force, right? We're looking from just the transfer to the stores. Short little video clip here just to kind of make a little bit more sense of all this.
This is the work energy theorem experiment. Here are the little cars. This is the little car that I talked about. And if you just pull it back, you load the mechanism, and as you can see, if you pick it up, it'll release the potential energy as kinetic energy. Okay, so if I just put it down without doing that, I get no motion. So I have to do work to get kinetic energy. So what I have here is the car and the motion detector. The motion detector is hooked up to the computer, and it will give us a velocity time and a distance time graph. So what I'm going to do is turn the motion detector on, then I'm going to do the work on the car and let it go. So I turn it on. Here's the graphs we obtained from this run of the little car. The top graph, which is a red graph, shows a simple position time graph, and you can see that the car simply went away from the motion detector. Okay? As a matter of fact, it didn't even barely go 1.5 meters. The bottom graph is the more important graph. It started off here at 0, and as the car left, it sped up to its maximum kinetic energy. Right here, the maximum kinetic energy was equal to the potential energy at the beginning, which was in turn equal to the work that I did on the car. That's your work energy theorem. The rest, right here, is simply friction bringing the car to a stop. And notice it stopped in the same location that it started in.
Okay. So let's take a look at example 4A. Abby fires a 7-kilogram cannonball, and is fired, oh, that's bad grammar, from the surface at 55 meters per second at an angle of 35 degrees to the horizontal. What is the total kinetic energy at the peak of the trajectory? Now the hint first is we need to find the horizontal component of the velocity. So it's coming along this way. We just want to find the x only, right? 55 at an angle of 35 degrees, which means the horizontal component is 45 meters per second. 55 cos 35 is equal to 45 meters per second. Okay, so if we take 1/2 mv squared, the velocity is 45, which means it is 7,087.5 joules. Because the horizontal component is not changing. It's going to remain the same, assuming no air resistance. Right, so we'll call that 7.09 times 10 to the 3 joules. When we take a look at example B, we've got the same thing, but we want to know what the gravitational potential energy is at the peak of the trajectory, right? What is the gravitational energy? Okay, so what we first need to know is the height, which means we need to know the vertical component of the velocity. 55 sine 35 is equal to 31.5 meters per second. So, given the fact that this is accelerating due to gravity, we can find the height using vs squared is equal to vi squared plus 2ad. Right, we're plugging in our numbers. We're going to square the 31.5 and move it over. Divide both sides by 19.62 in order to get a height of 50.7 meters. Which means the potential energy at the top is going to be equal to the mass times the acceleration due to gravity times the height. That gets you 3,483 joules, right? Or 3.48 times 10 to the 3 joules. So the total kinetic energy at the peak of trajectory, we knew. Total potential energy, we were able to calculate. And the total mechanical energy here is the addition of both of them. Gets you 1.06 times 10 to the 4 joules. Now the amount of work done here is that total amount of energy we had before is transfer. Some of it is transferred to the potential, some of it is stayed in the kinetic. If you took the 55 meters per second, 1/2 mv squared, you should get the exact same answer. Now, if you got questions, please feel free to let me know. Take care and have a great day.